So what are we going to do if we have, for example, a weight on a spring, and then we decide to pull that weight down and release it? What do you think that weight's going to do? Well, that's going to go up and down over a period of time. Well, that motion that it's creating over time represents something we call a simple harmonic motion. And that graph, again, if we were able to graph its up and down over time, would graph into a sinusoidal curve. Given this, we're able to go ahead and explore this concept called simple harmonic motion. Simple harmonic motion looks at a couple of different forms. There's a sine and a cosine version. That usually depends on where the initial placement of that spring or that object is at. It has this idea where we have the amplitude times the function, cosine or sine, times omega times t. And then our amplitude is, again, the absolute value of that displacement. And it over a period where it goes through a cycle is 2 pi divided by omega. So I have an example here that I want to explore and figure out, well, what can we do and what can we understand in this particular example? So the experiment that we set up has a weight on a spring. This weight is going to be pulled down 4 inches. And then it's going to take a complete 6 seconds for it to complete one complete cycle. So based on information, can we develop a formula to model that displacement over time? All right, so first of all, I need to choose which of these two am I going to do? Well, since we mentioned that the spring is going to be, we're going to add some potential energy to it and stretch it down, its initial position is not going to be at 0. It's going to be at another number. In those cases, we'll typically use the cosine as the particular model we'll go with. All right, so we chose the cosine. After that, can we know its amplitude? Well, its amplitude is 4, and it's in the negative direction. So far I have distance. It's going to equal a negative 4, and it's a cosine, because that's the one we're choosing. From there, how do we determine its omega? We remember its period. And its period set, so it's going to require 6 seconds for it to complete an entire cycle. So we would have then 6 seconds equals 2 pi over omega. Solve that for omega, which becomes omega equals 2 pi over 6, reduces down to pi thirds. From there then, I know that my omega would be pi thirds, and it's a function of time, is how we have that defined. So based on this particular model, this particular experiment that we have going on here, that the distance can be modeled by negative 4 cosine pi thirds at any given moment of time. Now in the previous example, we learned that it took 6 seconds for it to complete one entire cycle. Well, that leads us to introduce to you another term called the frequency. And the frequency is talking about is, well, how many or how much of that cycle was completed every second. Well, if it took 6 seconds to complete a cycle, every second, the frequency became 1/6 of the way there. So we would describe frequency in that case as 1 over 6 or 1/6. Let's look at another example now that I have in front of me. Imagine I have a weight on a frictionless surface attached to a spring. It's given by its motion, or its simple harmonic motion is going to be described as d equals 10 times cosine pi over 6 t. And let's figure out some questions we can ask. Do you know what its amplitude is? What its total displacement will be? Well, that we already have defined for us in the question is this 10 will represent its amplitude. That's the greatest value that is going to be displaced from its equilibrium point. It's never going to be greater than 10. 10 will be the maximum point, so we call that its amplitude. Its frequency, let's figure out what frequency is here. Frequency is defined by omega over 2 pi. Omega in this case is my pi over a 6. So I'll have pi over 6 all over 2 pi. We can not reverse that, but simplify that compound fraction, which becomes pi over 6 equals 1 times 2 pi. Pi's cancel, and so my frequency becomes 1/12. So this cycle, every second, the cycle will complete 1/12 of a full cycle. And then its period, how long will it take for it to do one complete cycle? Well, we noticed over here that frequency is the reciprocal of period. So we can solve it one of two ways. One, we can identify and solve for the period, which is going to equal 2 pi over omega. 2 pi divided by pi over 6. Solve that out, and that's going to equal 12, which isn't a surprise because 12 is the reciprocal of 1 over 12. So this was an example of a way to introduce to you one other concept, frequency. So when we're looking at simple harmonic motion, let's look out for the amplitude, let's look out for its period, how long it takes to do a complete cycle, and then its frequency, how much of that period was done every unit time, usually in seconds. And the last thing you might need to do is decide, have an understanding again between, are you going to use a cosine or the sine function for a simple harmonic motion?